We are going to go ahead and get started. Welcome, everyone. Thank you so much for being here. My name is Susanna Kohler. I am the press officer of the AAS, and I am joined here by Carrie Hensley, the deputy press officer, and Ben Casses, the AAS media fellow. And we are thrilled to be here in Madison, Wisconsin for the 244th meeting of the American Astronomical Society. This is the first press conference of the meeting, so thank you very much to our presenters for being here and being the guinea pigs of all of our technical problems on the first day. And the title of this session is Disks, Atmospheres, and Astronomy from the Moon. Normally, I'm a little better at finding cohesive titles for sessions. Admittedly, this one is not super cohesive, but we are really excited to have all of you here in a hodgepodge of topics for the day. So the way this is going to work is we're going to go through and each presenter is going to present one at a time, and then we're going to go to a Q&A session jointly for the whole group afterwards. And those of you who are in the room are welcome to use the microphone at that point to ask your questions. Folks who are online, you can queue up your questions at any time using the Q&A feature, assuming that I have correctly enabled all of the permissions. And while I'm at it, I should make someone a co-host here so that I am not the only person able to fix things that go wrong.
Nothing will go wrong.
Nothing will go wrong. Nothing will go wrong. And then we'll get to those questions when we go to the Q&A session. Reminder that we also have a Slack channel for the press conferences. So if you have further questions for our presenters today, you can enter them there later if you want to connect with them. And that is also where we're going to put our press kit, which will contain all of the press releases, the slides from our presenters, any further information there. So with all that said, am I forgetting anything before I introduce you all? Great. Here's hoping I'm not. Okay, so today we are going to be hearing first from Lisa Prato from Lowell Observatory, who's going to tell us about the topic of should I stay or should I go? What governs circumstellar disk lifetimes? I really appreciate that title, by the way. Then we're going to move online to our virtual presenter here, Christine Chen from Johns Hopkins University and Space Telescope Science Institute, who's presenting on the spectroscopic case for a recent giant collision around Beta Pic. Then we'll hear from Thomas Beatty from University of Wisconsin-Madison about results from JWST observations of a feature-rich sub-Neptune atmosphere. And lastly, we'll be hearing from Jack Burns from the University of Colorado Boulder, which is where I did my PhD, so I have a special affinity for it, about the dawn of radio astronomy from the moon, ROLSES on intuitive machines Odysseus's lander. So with that, we're going to go ahead and I am going to make sure to share my screen here. And with any luck now, we're going to be able to access the presentations. Maybe. Yes. All right, Lisa.
Good morning. So I'm going to talk to you about some things about primordial circumstellar disks around young stars. And these are very important because of the sites of planet formation. I'll comment on that in a minute. I have this little cartoon off on the left side of this first slide showing something very important. We have a lot of single stars. In fact, most systems are single, but most stars live in binary systems. So if you do the math on the little things in the ellipses, those are bound binary star systems. And you have most of your stars are in binaries. So binaries are important, and I'm going to talk about them. Taylor Kutra and my postdoc and Ben Toffelmeyer, postdoc at UT Austin, have done a lot of work on this, along with our other most excellent collaborators there. So circumstellar disks, they're the natural outcome of star formation. Star formation takes place deep in these giant molecular clouds, these dusty clouds, and deep down in the cores where it's cool enough for gravitational collapse to occur, we have star formation, and this rotation of these giant clouds naturally leads to these circumstellar disks. And in the disks, planets are forming. We've seen this now with PDS 70, which I show over on the right-hand side of this plot. What happens when you have binaries? It's kind of a mess. So what's going on with planet formation in binary systems? And remember, it's important. Binaries, many stars are in binaries. Most stars live in binary systems. Single systems have a very interesting problem. So if we just put a binary aside for a minute, the lifetimes of circumstellar disks, primordial disks where the planets are forming, sometimes they dissipate very quickly. They're gone in 1 million years. Sometimes they stick around for 10 million years. We don't fully understand what triggers that dissipation. Yes, they're mostly gone in 10 million years, but what is the source of that? What starts that dissipation happening? And this is really important because this is the raw materials for planet formation, right? Think PDS 70. Okay, so I thought I'll use binaries to understand better the dissipation in these circumstellar disks. And I had this little control sample. So I'll look at the stars and the disks and binaries, and it's a control sample because you automatically, it's like twins, people who study twins and then how twins evolve and how they age and so on. So it's like looking at these stars are not identical twins, but they have that same environment, the same age, the same composition. They're formed from the same cores. They have the same radiation environment. So all these things are very, very similar. So it gives you this little controlled experiment. FO tau we published earlier this year. It's a binary with an orbit of about 100 years. DF tau, we've been tracking this. I mean, these plots take many years, and they take exceptionally sort of high technology observations to resolve the two stars. These dots on these binary orbits were taken with adaptive optics and very large telescopes and very sort of cutting edge high angular resolution techniques over many years. DF tau, Taylor Kutra is about to submit a paper on this. And so we thought, okay, well, DF tau and FO tau, they're two very close binaries. They have relatively short periods. We looked at them. I have this survey, this study that I have ongoing at Keck. For years, I've been observing the individual spectra of these very close binaries with adaptive optics in the infrared to determine the stellar properties. And so in these plots, on the top is the primary star, on the bottom is the secondary star, and the black lines are the actual data, and then the colored lines superimposed are model fits. And we've developed this model grid so we can determine temperatures, we can determine the surface gravity, the fluffiness, that's a measure of age of a young star, rotation velocity, magnetic field strength, and get all this great information from high resolution spectra. And Keck has the angular resolution because it's 10 meters. Keck 2, you can actually get down and see the individual components in these very, very close binaries. And so you can also look at the excess that's in these stars from near very close dust, warm dust grains close to the star. Notice that the bottom spectrum in DF tau, the secondary, notice that those lines are sort of broad. All 4 of these stars have temperatures about 3,500, 3,600 Kelvin, and they have similar rotation, similar surface gravities. The magnetic field strengths are 2 or 3, 1 to 2 kilogauss. But that DF tau secondary is sort of those broad lines indicate that it's rotating very, very rapidly. And it also has no excess. There's no sort of filling in, veiling, we call it, of the secondary star spectrum. So we thought there's probably only one disk in the DF tau system. How interesting is that? Now we can look and see what the differences are in these two stars and why one of them has a disk and why the other disk dissipated. You can see this energy distribution from a paper by Tom Allen a few years ago. All the way on the left-hand side, there's this in the primary, the blue squares, that's an ultraviolet excess, and that shows active accretion from the disk onto the primary star. Secondary doesn't have that, the red circles. In the near infrared and towards the right of that plot, again, the primary has that excess, those warm dust grains, and so it's got a disk right up to the star, whereas the secondary does not have that. So we thought, okay, let's use ALMA. Let's look at the details of that very groovy disk around the primary. And what did we find? We found 2 disks. So the secondary star has a disk, but there's a gap in the middle. And remember, that's the star that's rotating very fast. Its spectral lines are very broad. And so there's something different about that star. So our puzzle now, in this publication we're about to submit, is to tease out what is the reason why that disk has started to detach from that secondary star. FO tau, well-behaved, both disks are there, they're accreting, they're aligned with each other, they're aligned with the orbit. And so that might be a big hint. We believe that the DF tau secondary may be misaligned, the star with its disk, the disk potentially with its orbit. And so it's these dynamical effects that may play a role in the onset of disk dissipation. And hopefully when we get to the entire sample, we keep getting stuck on these very interesting single cases. But when we analyze the entire sample together, hopefully that will provide more insight. And I just want to make the point that Keck and ALMA yield very, very powerful combination. This is an artist's concept of how that system might look. Shout out to my team, Disks Exoplanets Flagstaff team. Taylor Kutra is second from the left on there. She's the postdoc who will be the lead on this paper. Thank you so much.
All right, so Christine, if you want to go ahead and start screen sharing and then give me a second to just move the window around.
Does my screen look okay?
I don't see it yet.
Oh, it says it's sharing. Let me try again. Do you see it?
Yes.
Great.
Hang on. Just a sec. Okay, I think we're good. Go ahead.
Thank you so much. I'm really excited to be here today to give you the spectroscopic case for a giant collision in the Beta Pictoris debris disk. This disk is a slightly older evolutionary state than the systems that Lisa just spoke about. In this debris disk, most of the gas and dust that forms the protoplanetary disk has dissipated, and we've formed large objects, including planets, giant planets. And here you can see some artist renditions of asteroids and comets, and they're banging into each other and creating dust. I particularly would like to give a shout out to two people who've contributed very strongly to this project. One is Cicero Liu, who is currently a science fellow at Gemini North Observatory, and Caden Worthen, who is a graduate student at Johns Hopkins University finishing his third year. And there are many other contributing authors. Uh-oh, there we go. Okay, like many science projects, there's a little bit of a human interest aspect to this story, this evidence for a giant collision, in that this was found serendipitously. So about 20 years ago, I was studying Beta Pictoris with the Spitzer Space Telescope, and we found several different dust populations. And so I was super excited to reobserve this system in 2023 using the James Webb Space Telescope. And I was really hoping to understand the planetary system in much greater detail, and we are definitely doing that. But one of the big surprises that we had when our data came down in January 2023 was that two of the dust components that we had seen in the Spitzer data from 2024 to 5 had disappeared. So this is a little bit different from some of the other JWST results that you'll hear about, where they're talking about what new observations reveal. I'm going to be talking about what the new observations didn't reveal. So this was really an unexpected observation that's changed our understanding of the planetary system and leads us to believe that there's been a recent giant collision in this system. So just as a reminder, Beta Pictoris is, I would call it, a teenage planetary system. That means that it is still forming its partially formed its planetary system, but it's not done yet. So we know based on ground-based observations that there are two giant planets in this system, Beta Pic B and C, located about 10 and 2.7 AU away from the star. And there's also exocomets and asteroids, and they're banging into each other, and by those processes forming terrestrial planets and also creating dust debris. So this is what our observation looks like. It was obtained with JWST using the MIRI medium resolution spectrograph. This particular instrument observes in the mid-infrared and it produces pictures and spectra at the very same time. And so on the left-hand side, you can see a picture that was taken at about 15 microns of the inner part of this planetary system. This picture shows you where the red star is. That is where the host star is located. And then you see a bright band that goes up and down across the image, and that is the dust in this system. So what's basically happening is that starlight is shining onto the dust and warming it up. And so it's radiating heat and also solid state spectral features from dust grains that are in the planetary system. So the right-hand side shows the comparison between the 2004-5 Spitzer IRS spectrum and the 2023 JWST MIRI spectrum. And you can see that they are really vastly different. In the blue spectrum, you can see some very notable things that are now missing from the JWST data. Specifically, you can see there are peaks at 18 and 23 microns. These are due to very small, cold, forsterite dust grains. And then you can also see at the shorter wavelength end of the spectrum between 5 and 15 microns that the overall level of the spectrum has decreased. And so that this is indicating to us that there used to be hot dust around this system, which has since disappeared. So I just wanted to have a quick reminder about crystalline forsterite. Crystalline forsterite is a material that we're familiar with and is on Earth. If you've ever been to the green sand beach at South Point on the Big Island of Hawaii, you will find sand on the beach that's composed of olivine or crystalline forsterite. There's a pretty picture of what one very large crystal looks like on the bottom right-hand side. The chemical formula for this is Mg2SiO4. And if your birth gemstone is peridot, then you have a little piece of crystalline forsterite. So how do we go from this spectrum that has these extra dust populations to one that does not? Well, what we think is happening is that radiation pressure is removing small dust grains, and that those features are from very small dust grains. So in this particular case, these very small dust grains, they feel a force due to radiation pressure from the star, the light pushing on the small dust grains. The bigger grains are immune to this mechanism because they have more mass, and so they can remain bound and continue to orbit around the star. So really, this observation is changing the way we think about this planetary system. In general, we always, as astronomers, think that systems are in steady state because if we think about how we view the universe, human lifetimes are very short compared to the age of the universe. And so when we look at the stars or planet formation, we assume that we're not looking at it at a very special time. But really, what we're forced to do here is to change our picture because the system is not in steady state. The spectrum has changed a lot. And so now we think that this system is really dynamic and changing. So this is really building evidence for a collisionally active planetary system. There have been a couple other pieces of evidence that this system is active. In 2014, ALMA discovered carbon monoxide gas in this system. That's really interesting because the carbon monoxide gas does not have a very long lifetime around the star. It gets destroyed by the star's sunlight in about 100 years. And the system, again, it has an age of maybe 20 million years instead. So we know that that CO, that carbon monoxide, must have been created recently. And a plausible explanation is that collisions between icy planetesimals and the outer part of that planetary system liberating the carbon monoxide gas. Another result that you may have heard about, which was just released 6 months ago, is another JWST result, but now with imaging. And this is a picture that was taken with the MIRI coronagraph showing a new structure called the cat's tail. In this case, the cat's tail is hypothesized to have been created by a giant collision much further out in the disk at much longer ago, so 85 AU, and about 150 years ago. So we think that there's quite a bit of evidence that this is an active system. So just in summary, we think that Beta Pictoris has experienced a recent giant collision. It probably occurred just prior to the Spitzer IRS observations 20 years ago. And that collision released It pulverized a really large solar system asteroid. Stellar radiation pressure blew the dust out of the planetary system. The dust clouds swept through the planetary system and could have impacted the giant planets within it. But for me, most excitingly, is the continued access to the infrared and the picture that JWST is able to provide us with witnessing terrestrial planet formation. Thanks for your time and attention.
Mine might bounce again.
Oh, that's true.
Yeah, because this is what I get for using fancy fonts. All right, thank you. All right, good morning. Actually, Susanna, I think actually this session is going to fit together pretty well. Yeah. Because I'd like to tell you today about JWST observations of GJ 3470, which is a Sub-Neptune, cool Sub-Neptune exoplanet, and the feature-rich transmission spectrum that we saw. And I wanted to start with, and this is why I think the session fits together pretty well, with why we want to measure the composition of exoplanet atmospheres. And there's a bunch of reasons, but one of the fundamental reasons to me that we want to measure exoplanet atmosphere compositions is we want to understand planet formation. How do we go from observations of protoplanetary disks, like Lisa and Christine were describing, to planets? How do we understand that process? And the analogy I like to use is if you were baking a cake, right, and the protoplanetary disks are all the ingredients laid out in front of you, and the planets are the final cake come out of the oven, how do we actually understand the recipe that went into that without being able to see the baker actually make this cake? So one of the ways you could think about doing this is we need to measure what's inside the cake. We need to eat the cake and figure out what's inside of it so we can understand the ingredients that went into it. And to do that, we need to understand the compositions of exoplanets. What is inside of them? What is the end state of the planet formation process? So for the last decade, the two main ingredients that astronomers have looked for have been carbon and oxygen. There's been a lot of papers about carbon to oxygen ratios and exoplanet atmospheres. And this has been seen in a bunch of places. In particular, as we're thinking about smaller exoplanets that are the dominant outcome of planet formation, the smallest kinds of exoplanets in the universe are sub-Neptunes, which are very small gas planets. Two of these, TOI 270d and K218b, we have from JWST good carbon and oxygen detections, where we've been able, we think, to get a good C to O ratio for the atmosphere. But there are many other possible ingredients to look for, right? There's a lot of other atoms that we could think about looking for, in particular, for what I'm going to talk to you about today, sulfur. So what we did is we looked at GJ 3470b, which you can see it right there. It's about half the size of Neptune, maybe. Same radius, but about half the mass. And this has been observed before by Hubble and Spitzer, and they got a very nice detection of water in the atmosphere. We observed two transits of 3470 using the NIRCam instrument on JWST and get what we think are very nice spectral features. So we get a good detection of water, good detection of methane, less than you would expect, and carbon monoxide and dioxide, and one more surprise, right? This bump right here, which ends up being SO2 sulfur dioxide. Which was very exciting because sulfur dioxide has been seen before in exoplanet atmospheres. We saw it in WASP-39 with the ERS observations, but this is WASP-39 is a planet that is twice as hot as 3470, and it is about 100 times more massive. So it's fundamentally a different kind of planet than what we're looking at with 3470. And in particular, at the temperature that GJ 3470 is at, we actually did not expect to see sulfur dioxide. This is a plot from a theory paper that came from WASP-39. You can see at the expected value for the temperature of 3470 at about 600 degrees, the expected value is off the bottom of the plot. Where we actually measured it was also off the plot, but it was off the top of the plot. So that's about 1 million times more SO2 than you would have guessed based on that one modeling effort. So what this means, right, is we now have a detection of sulfur in a very small and cool exoplanet atmosphere. Sub-Neptunes are one of the most numerous kinds of planets in the universe. They're one of the dominant outcomes of planet formation. And so this is exciting because this gives us one more element, one more ingredient that we can try and use to trace the recipe of the planet formation process, right? Have our cake and maybe eat it too. So I'll leave the summary up here. But one thing I also want to mention, besides just being exciting because it gives us, a new recipe for, a new way to understand planet formation, is I think this also really is a foot in the door to using JWST observations to understand planet formation. One of the big goals, I think, of the early years of JWST will be using compositions to understand formation mechanisms. And this is, to us, a very exciting result because I think there's going to be a lot of good future work, hopefully using these measurements we just made to really understand for this system how this planet formed. So thank you.
All right. Good morning, everybody. I may even be able to tie this one in to the other three. We'll see. We'll see as we progress through. But it has been over 50 years since NASA last landed a scientific payload on the moon. That changed in February, in which the Intuitive Machines lander, funded by NASA's Commercial Lunar Payload Services Program, it soft landed the first radio telescope on the moon funded by NASA called ROLSES. I'm going to talk about that today. I'm going to talk about the mission, and I'm going to talk about the first results from ROLSES. But first, some cool pictures of the launch and transit. Here is a picture of our lander inside the payload fairing of the Falcon 9, and you can actually see a bit of the housing for one of the 4 monopole antennas that make up the ROLSES radiometer. And then this cool picture of our launch just hours before the launch, Falcon 9. I particularly like this because you can see our destination in the background, which is the moon. And then a video following a picture-perfect launch. We were deployed, our lander was deployed from the second stage, as you can see here. Once again, that went very smoothly, and we were off on our way towards the moon. A few bumps along the way. We had some problems with the star tracker. Initially had to do some rebooting, but that was okay. But also along the way, about 6,000 miles before landing or away from the moon, we got a message saying one of our antennas deployed, which was not supposed to happen. And we actually got a selfie of that. And you can see our monopole antenna, which is 2.5 meters in length, is deployed from the lander. And so we took advantage of that, turned on our radio spectrometer, and we got some data. And here's the kind of data that we expected from the instrument. This is raw now, so no calibrations, no attempt to remove backgrounds. But the data that you're looking at here is called a dynamic spectrum. This is frequency versus time, and we've got about 1.5 hours of data in total. But what I wanted to point out there are some of the red horizontal lines that you see going across there. That's the Earth. Those are transmitters coming from the Earth. We got a good picture, a good selfie of the Earth taken from a unique perspective on the way to the moon. I'll come back to this a little bit later with a much cleaned up, much improved version. Our landing site is called Malaparte A, is about 10 degrees from the south pole of the moon. NASA wanted to go near the south pole, but not too close, because if we crash, we didn't want to pollute the Artemis sites. Think of the Shackleton crater as basically the south pole of the moon, as you can see in the bottom. And then another picture, this one taken actually by one of the commercial payloads, so a non-NASA funded payload from the International Lunar Observatory in Hawaii. And you can see the Malaparte A crater, which is in shadow at the South Pole. The moon is very low on the horizon, so we get these very deep shadows as we're coming in. And then another selfie just after landing. But we got an oops here. Because we came in too hot. The reason being that our laser guided navigation system was not functioning. So we had to rely instead on optical imaging, which was actually a pretty heroic effort to get onto the surface. But we came in hot, too fast, a little bit too fast, and also with a little bit of horizontal velocity. And that resulted in one of the landing legs breaking. That you see over here. The rest of them, the actuators absorbed the landing pretty well. But that oops resulted in us tipping over. As you see over here on the left-hand side is actually another selfie taken on the moon of the lander. We're tilted over about 30 degrees with respect to the surface, and also an illustration of that by Steve Ultimus, the CEO of Intuitive Machines, during a press conference, showing you what that looks like. But all was not lost. Oh, I want to show you this picture. This is a picture taken from orbit of the Odysseus lander by the NASA Lunar Reconnaissance Orbiter. You can see in the upper left, the crater. We only have a couple pixels across for the lander, but you can see that we're actually there on the moon. Now, I was going to say our radio spectrometer is called ROLSES, and you can see it's actually an acronym. And what we had hoped that this would look like is in the upper left, and you can see two of the four monopole antennas sticking out. Those antennas are called stasers. They're spring-loaded antennas. We simply open up and they pop out. 2.5 meters in length, but they are temperature sensitive, as we found out, at least on one of them. And then the digital spectrometer board. The instrument itself operated over 2 bands, a very low frequency band from 2 kilohertz to 1 megahertz, and then a higher frequency band from 300 kilohertz, roughly 1 megahertz, to 30 megahertz, all of which are below the what we can effectively do from the Earth, and below mostly the ionosphere cutoff. All right, so here's the cleaned up data that I wanted to show you. This is our first data product. There's still a lot of processing to go, and you can see on the left-hand side is the data I showed you originally in transit, much cleaned up. And so now we get a really good frequency selfie of the Earth. We see a detailed frequency spectrum that really is unparalleled to date in terms of looking at the Earth's spectrum. On the right-hand side is a similar spectrum taken from the moon with the same antenna, but here we only have about 20 minutes worth of data. So it's low signal noise, but nonetheless, there's a few of the same spectral lines that we can see. So what can we do with that? There's more science to be done potentially here, but with this data looking at the Earth is we can redo the Sagan experiment from 1993 with a much improved radio spectrum. Sagan used the Galileo spacecraft when it did a flyby of the Earth on its way to Jupiter with the idea of doing a control experiment, looking at the Earth, in other words, as an exoplanet. Here's our connection to exoplanets, okay? So looking at the Earth as an exoplanet and producing a much improved spectrum. You see the Sagan et al. Spectrum in the upper right, and they basically have just the one line versus our much richer spectrum at a higher frequency that we're able to analyze. So we have improved time resolution, we have improved spectrum, frequency band, dynamic range, and also importantly, as a control experiment, what we're looking forward to is comparing this Earth spectrum to ones of nearby exoplanets that we hope to observe with our far side array of radio telescopes This far side was funded by NASA Astrophysics a few years ago for a design study, 256 dipole antennas. And with that, we'll be able to look at about 2,000 nearby exoplanet systems. And so again, now we have from Earth, we have a control that we can look at. So I'm going to stop there, and I'll just say that put the lessons learned up there. The cool thing about this CLIPS program is we have an ability to refly. In fact, NASA has already funded us to refly an upgraded ROLSES in 2026 with some of the upgrades that I've listed over here that will allow us to address some of the unsampled science that we were unable to do with ROLSES 1. So I will stop there. Thank you.
Wonderful. Thank you so much to all of our speakers. So with that, we will go ahead and move into a Q&A session. So let me see. What do I need to display? We want Christine to join us in the room. Okay. So any questions in the room? Go ahead and raise your hand, and Carrie will bring the mic around to you. And Ben, if you have any questions online also, you do. Okay, Ben's got one.
Sure. This is an online question from R. Mark Elowitz for Jack Burns. Is there any way to decode the terrestrial transmissions, aka technosignatures, to determine the content of the transmissions from Earth?
Yeah, that's a very good question. And so we're beginning to analyze that. And we're going to dig in a little bit more. We also have some ground-based data that was taken at the same time. The ground-based data is more limited because you have access only to a relatively small number of transmitters. From the moon, we have the entire Earth that we can sample. So we're in that process, and technosignatures is exactly the right description here of what we're looking to be able to produce for the Earth as an exoplanet for a comparison to other nearby exoplanets.
I have a question for Lisa. You mentioned that with the disk that you're seeing a gap in, that it was evidence of detachment. And I'm wondering why that's the assumption as opposed to anything else creating that. Yes, should be able to just talk into it.
Okay. Yeah.
Mhm.
So a detachment, maybe it's a sort of ambiguity of terminology, because detachment it sort of implies the unlocking of a disk. The inner parts of disks are very slightly ionized, but to such a degree that these very strong magnetic fields, like I mentioned, the magnetic fields are about 2 kilogauss from the young star. The field can lock onto the disk, and the disk can actually regulate the angular momentum of the star. And so when we see a star spun up and a gap, evidence for a gap in the inner part of the disk, that's sort of the detachment that I was referring to, the disk unlocking. And that's one of the things that can allow the star to spin up. But there's a kind of a chicken and egg problem here. Did the star, for some reason, spin up and break the lock, or did the lock dissipate, the disk dissipate and unlock, and the star spun up? So we'll be working on that.
Thank you.
Hello, I have a question for Mr. Burns. So this seems
And I should have mentioned, sorry, could you identify yourself and your affiliation, please?
right. So I am an undergraduate student of physics at Michigan Technological University. I'll be presenting in just a couple minutes. So this is an important first step regarding astronomy on a different body other than the Earth or around orbit. So with the Artemis program and many private industries taking flight, do you see what does the future of astronomy on the moon look like to you? This is an important first step. So what are the next steps?
Yeah, it's a complex future. I mean, obviously with Artemis, a lot of us have been fighting this battle to get back to the moon for over 40 years and get a radio telescope on the moon. And so it's taken a long time. So we have that first step. The next steps after that, we have several more mission ROLSES 2, and then one called Lucy Night, which is going to the far side also in 2026 to begin to do some cosmology. Following that are arrays of radio telescopes on the far side, which will have some spatial resolution as well as much improved sensitivity. And that opens up a wide variety of science, including looking for both naturally occurring radio emissions from exoplanets, namely cyclotron maser emission coming from the magnetic fields. So we'll actually be able to contribute to understanding habitability of exoplanets by detecting those with magnetic fields that might have some shielding, as well as actually measuring those magnetic fields. And then the technosignatures we were just talking about.
Mark Astro with Astronomy magazine. This is for Jack. I was wondering if you could talk a little bit more about how the harder than expected landing and the resulting orientation affected the ROLSES experiment.
Yeah, it affected a lot. First and foremost, we were supposed to have 8 days worth of data. We ended up with an hour and a half to 2 hours worth of data total. So much, much less. And of course, that affects the signal to noise. But really, I look at this was a heroic landing by the Intuitive Machines folks, because they did not have their primary navigation system working. And to be able to set down softly on the moon, even with a broken leg, was pretty amazing. And then on top of it, the high gain antenna was looking at the dirt. So we had to use the low gain antennas to transmit data, and also those partial shielding of the solar panels. So we had limited power. Still able to deploy our antennas, still get some data back. So when I tell my students, don't be terribly disappointed, because we did get some data, and we've learned a lot about the system in looking at that data. And excitingly, we've got a next flight coming up in just 2 years.
All right. I have a question from Ethan Siegel from Starts with a Bang on Big Think. And this is for Lisa and Christine. Where is the transition line between circumstellar planet-forming disks, like the kind Lisa observes, and later time debris disks like those found around Beta Pic? How long can a circumstellar disk last, and what defines the first appearance of a debris disk?
That's great. I'll start, Christine, and then you jump in, because that's how the ages go. So the primordial disks are present in the first roughly 10 million years, and they evolve in that time. That our sort of typical picture was that the gas gets all dissipated more rapidly, accreted and photoevaporated and dissipated and tied up in planet formation. But as Christine said, they found CO around Beta Pic. So, and I think this has been a trend that we've been seeing for many years. There's more and more evidence for some remnant gas in these disks. So whether you can form some gas giants or build up some gas giants at later times than we had initially expected, I think is an open question. And then there's problems with how we form hot Jupiters. That actually is sort of the other end, of the planet formation scale. These very, very, very massive planets could be up to several Jupiter masses, very close to the stars with 2-day periods, orbital periods. How do those form? And so one answer is those could have started to form way back when the system was still very embedded and we couldn't even see it. And so there are these rough constraints, these sort of limitations we can put on the timescales. But a separate project I'm doing is looking for planets around these extremely young stars with disks, and it's excruciatingly difficult. And all of the ones that have been identified are under question, except for PDS 70. And so that's exactly what I'm trying to get at with that other project, is to understand how long it takes to form observable planets, and are they already forming much earlier than we had anticipated. And yeah, I think Christine can now speak to sort of later stages.
Yeah, I want to amplify and maybe slightly refine what Lisa's saying. So the key defining characteristic between the two kinds of objects is the amount of gas. And so basically protoplanetary disks have much more gas. They have a lot more, not just CO, which we see, but we presume that they probably also have molecular hydrogen as well. And this is sort of left over from the formation of the star. This is primordial material. Debris disks are fundamentally different because the gas is much dissipated. So if there's 100 times by mass more gas than dust in a protoplanetary disk, we think in debris disks, the ratio is more like 1-to-1, right? And that the gas that you're seeing is not primordial. It's actually what I would call second generation, just like the dust. That is to say that it's not left over from star formation, but it's actually the CO has been incorporated, for example, in clathrates and ices. And when you have collisions between planetesimals like comets, it releases the gas, and that's how we see it. Or at least that's one of our primary explanations right now for why there is gas in debris disks, is that it's collisionally generated rather than primordial. So I think across the two different topics, we're all interested in studying planet formation. And as Lisa said, like the transition is probably in the 5 to 10 million year range. We date that by looking at accretion of gas from the protoplanetary disk onto the star. And the gas accretion typically stops in that age range, about 5 to 10 million years. So we think that by the time you get to these debris disks, that giant planets have formed. But if you look at our solar system, it takes another 100 million, 200 million years to complete terrestrial planet formation. So that's why I referred to them as teenage planetary systems, is because the gas giants are there, but the terrestrial planets are still forming. So I hope that helps.
The question over here.
Thank you. I have a question about like building the radio telescope around the far side of the moon. I'm sorry, I'm from University of Michigan. I forgot my nameplate. Like, is NASA planning to shoot a relay satellite on the far side of the moon, because it's the far side. You can't communicate directly from the Earth to the far side of the moon, so we sort of need a relay satellite. Is that a planned mission? Or?
Yes, yeah, that's a good question. The answer is yes. As part of our Lucy Night mission going to the far side in 2026, we're going to carry with us a communication satellite that we will place in lunar orbit so we can transmit the data in the comms back, as well as also a radio beacon that we'll put in orbit that will help us map our radio beam and help us to remove some of the foreground that we're looking at as well. So you're absolutely right. You have to have that in order to be able to operate from the far side. The Chinese Chang'e 6 mission similarly placed a comm satellite so that recently when it landed on the far side in the South Pole Aitken Basin, it was able to communicate with its lander.
This is a question for Christine from Monica Young of Sky and Telescope. Exocomets have previously been observed transiting Beta Pic in test data. With your reported collision, it makes me wonder, how many collisions could we expect to happen in the disk around this star? Could we expect to see it happen again on human timescales, and maybe this time have JWST watching?
That's a fabulous question, and that really points to something that we don't understand. Absolutely, TESS has observed an exocomet around the star, and even prior to TESS, we had seen time variable calcium 2H and K absorption features that told us that those exocomets existed, and they've been monitored all the way back to maybe the 1980s. And we see these exocomets infalling into like Beta Pic on timescales as fast as hours, but we see them on hours, daily, monthly, all sorts of timescales. And I think this just really highlights how little we have studied these systems in the time domain because we really don't know what's happened between 2004, 5 and 2023. Like, maybe another collision happened and, we just weren't able to catch it. So I'm definitely very hopeful that we can do some time monitoring and then learn more about the frequency of these events. Thanks for your question.
Are there any more online? Yes, absolutely.
This is for Thomas. I am very curious.
Yes, Lisa.
Sorry, I'm very curious that about that. I mean, it just blows my mind. SO2 is 1,000,000 times more abundant than you expected. Two parts to the question. One, that do you have any ideas for what that could be? And are you observing other systems? Are there other systems where you think you could detect such abundances with such high signal to noise?
Yeah, so that's a good question. So one of the actually, to me, outstanding, intriguing uncertainties in all of this is that the production pathways for SO2 on exoplanets is actually relatively poorly understood. Because there's a lot of chemical reactions that go into producing SO2, and identifying which are the most efficient is something that a lot of people are working on right now. And so that's part of why that plot I showed you, the expected value is off the bottom for where we were looking, is because now with these observations, it's one of these things where once you know that, we saw a lot of SO2, how could we get there? Then we went back and identified that actually it was because, we have a lot more, it's a much higher metallicity atmosphere. There's a lot of carbon and oxygen in the atmosphere that isn't present on WASP 69. And so once you account for that, then there's, some chemical reactions occur more rapidly. And so that allows you to produce all this SO2 on the day side. It's produced photochemically by UV light from the star, blasting apart atoms. So yeah, I think we're thinking about other candidate planets, but at the moment, our understanding of this, I think, is poor enough that it's difficult to come up with a target list at the moment. It's sort of, we're going to look at some hopeful planets and see what we get. But why there's SO2 on 3470 but not POI 270b, the other planets in this parameter space, we don't understand.
I'm really glad you asked that, Lisa, because I was dying to know. All right, are there any more questions in the room or online?
That's Christine.
Absolutely.
Christine, can you get like a lot of JWST time and keep observing for like the next 20 years? Because I mean, it seems like this is a time domain project, right? And more practically, are there ground-based facilities you can use to try to eke out some of this time domain without spending all the JWST time yourself?
Yeah, so that's a great question, right? So one of the real challenges about the mid-infrared and the reason why JWST is in space is because there are particular atmospheric windows that we can see through and other places where we cannot. And so in particular, that 18 and 23 micron, the 18 micron feature is in an area where we can't see the sky. And the 23, it's hard to do from the ground with good signal to noise. Probably the most equivalent kind of thing is Vizier on the VLT, but I don't think it does Q-band spectroscopy anymore. So I think this is a project, unfortunately, that has to pretty much be done from space. As you said, so I work for JWST, so I can tell you that the oversubscription rate on proposals was horrendous for cycle 3. It was 9 to 1. But there is I think a recognition that time domain astronomy is a really important topic generally. And so the director's office here has 2 large projects that it's soliciting input from the community to define. One is a 500-hour program on exoplanets, which is going to be focusing on the cosmic shoreline. But the other project is 500 hours for transient science. And that's been broken down to a lot of different topics, mostly extragalactic, looking at supernovae and things like that. So unfortunately, this particular time domain thing did not fall into the purview of the director's working group. But so it's a thing that we'll have to pursue through open time. But I think it's a very interesting thing and definitely worth following up on, for sure.
Great. Any last questions? All right. Well, these were wonderful presentations. Thank you so much again to our speakers for this great series. And thank you for tying them together so beautifully in a way that I did not succeed. That was great. Thank you to all of your PIOs for helping with press releases and visuals and all of that. And thank you so much to all of you in the audience for coming to this. We hope you'll come back again. The next press conference is going to be this afternoon at 2:15. And the title of that is Stars and Their Antics. So we hope you'll be back. We'll be here all week. We've got the press kit online if you need resources, materials, and we'll see you later. Thanks again.
Thank you.